Welcome, ladies and gentlemen, to the forum of the group exhibit Hydrogen and Fuel Cells here on Hannover Fair. I would like to invite you to take a place here, have a drink on the house and discuss with us with our next interview partner here on stage from BASF from Ludwigshafen in Germany. We will talk about new Celtec MEA and the next MEA generation. I would like to introduce to you the head of Global Fuel Cell Coordination and Research Center of BASF in Ludwigshafen, Germany, Dr. Carsten Henschel. Dr. Henschel, may I ask you to step up the stage? Thank you very much. It's a pleasure to have you here. Yeah, we will talk about MEAs, and you will always have the opportunity to raise your hand and ask your questions. If you have a question, just show it to me, so I will come with a microphone to you. Dr. Henschel, BASF in Germany and probably all over the world, everybody knows BASF. It is, except of other things, the leading industrial supplier of the membrane electrode assembly, the MEAs we are talking about, for high temperature PEM fuel cells. That is something BASF is really strong in it, isn't it?
It is indeed. I mean, if you look at the vast portfolio of BASF, they have activities as chemical company and material suppliers in all areas, from mobility, living, health, everything. And one of the big areas they are looking in is energy. And we have a lot of activities now in lithium-ion batteries and all kind of other batteries, next generations, and like wind energy, solar panels, all kind of activities. And fuel cells is just one of it, but I personally think certainly one of the more interesting ones. And BASF has a big advantage of being a huge and experienced catalyst producer, of having a lot of expertise and industrial capacities in polymer science and membrane development, and last but not least also in electrodes, gas diffusion material. So we can really integrate, combine it together, and have a strong sort of internal value chain to produce, develop and market our MEAs for high temperature PEM fuel cells.
So when you're concentrating on MEAs for high temperature PEM fuel cells, you probably believe in high temperature fuel cells. You can find them always when you have a fuel processor before it, when you use like methanol or natural gas or a diesel even, and you produce the hydrogen and then put it into the high temperature PEM fuel cells.
Yeah, that's the charm of the high temperature PEM fuel cell. I mean, there are a lot of activities, a lot of areas where you can use fuel cells, and low temperature PEM fuel cells based on hydrogen. They have a lot of advantages, performance density, you have a lot of experience in data. But indeed, when it comes to the situation that you don't have hydrogen handy, if you have to rely on natural gas, on LPG, on any sort of carbon materials that you first have to process to have your hydrogen, then high temperature PEM fuels have a lot of advantages. You don't need a very complicated gas processor. You can really use even a rather dirty hydrogen with a lot of carbon monoxide in it, or even sulfur.
Much more tolerant against the carbon monoxide or sulfur or something like that.
Right, it just makes life easier for the system builder. And in addition, you can also thermally integrate the reformer and the stack much better, and doing so increase the overall efficiency of your system and of your processor. It can really make a lot of difference.
So what temperature we are talking about? If you have the gas reforming process, it runs on several hundred degrees Celsius, and the high temperature fuel cells on what degree?
It's around 160.
160, okay.
And
so that's easier to cope with than at a low temperature, which runs on 50 or 60 degrees.
Right, exactly. And you even can use the heat of the stack to make your processor more efficient. You can preheat the gases that go into the gas processor.
And also, you don't need any water management with high temperature PEM fuel cells. Why not?
Isn't that wonderful?
Yeah,
we have our electrolyte on board, so to speak. So we have phosphoric acid that is responsible for conducting the protons, not water. That's why we can operate at 120, 40, 60 degrees Celsius when water is vapor, actually, or steam.
So it's obviously an increasedness in robustness and also in efficiency for the system if you use high temperature PEM fuel cells instead of low temperature fuel cells. But there are still some applications where they still use low temperature fuel cells, even for micro CHP. I just think of Baxi, who still use these low temperature fuel cells. They have to be convinced still. Eh?
Well, I'm always surprised that it's still there, but now, I mean, those companies, they have already developed a complete system, starting with a processor that can really produce very clean hydrogen with whatever, 5 or 10 ppm of carbon monoxide. And if you have everything already on board, then it's difficult for them to convince their own management to change to another technology. We just believe, if you start from scratch, if you really have to rethink your concept and your market, it makes a lot of sense to look into high temperature PEM fuel cell because you can indeed offer a more robust and much more efficient system if you can use the heat and yeah.
Of course, if you look only to gas reforming, if you use a high temperature PEM fuel cell, how much percentage can you save in comparison to a low temperature PEM? Could you say that?
Yeah, it's certainly difficult. I mean, this is a little beyond our or my competency. But what we heard from customers is they say we need 1/3 fewer components and more or less also the same about the cost.
Okay, huge advantages with high temperature PEMs. So let's talk a little bit about the typical applications. We already mentioned the micro CHP, combined heat and power systems, but also for uninterrupted power supply. It's a good opportunity, isn't it?
It is, indeed. But again, if you have a gas processor and you want to ensure this uninterrupted power supply for a long running time, for extended running time, then I think the high temperature PEM fuel cell makes a lot of sense. If you're looking for a system that can react within seconds and just run maybe for half an hour to sort of bridge an outage of your grid, then I think I would opt for the low temperature PEM fuel cell.
Okay, so you need still a little bit time until to get this temperature up.
Yes, and it's really for extended runtime. If you need to run it for maybe days, maybe even if you don't have a grid, that could be also an interesting concept.
Okay. Mm-hmm. Also for APUs, for auxiliary power units, it could be an interesting application.
Yes, it is. We have a couple of customers who have developed those products in small, like for recreational vehicles, but also larger for mobile applications, such as battery range extenders, so to charge up your batteries or your hybrid systems, even up to big ships, boats that are here displayed also on the Hannover Trade Fair.
So with the right reforming, you can also use diesel to reform the diesel to hydrogen and then produce energy in your hot temperature PEM fuel cells. That could end in electromobility without a hydrogen infrastructure.
Yeah, that could be indeed an alternative. If you still wait for the hydrogen infrastructure, this might be sort of a bridging technology. We can use the hydrocarbons that are around and the infrastructure that is around. But you have to really look into the development of the reformers as well. And diesel reforming is something quite difficult and challenging. And I don't think that anyone is already that far to really think about integrating such a reformer into a car.
So let's compare it also with SOFC, solid oxide fuel cells. They're running on even higher temperatures, are even more robust and maybe also even cheaper. So why do you think hot temperature PEMs are better?
Why do you think they are cheaper?
I thought so. They only have solid oxide. PEM also always have titanium and have platinum in it.
Well, not titanium, but anyway. I think if you
I've
look
looked
at
the bipolar plates, there's titanium in. Okay, never mind.
Yeah, not for PEM maybe. I think if you look at the whole system, and a good SOFC is still pretty expensive, and it takes a lot of experience in production technologies to get it really straight and consistent and reliable. We have seen a lot of progress within the last 5 years with this technology, but I still think it's it still has to develop some more before we can see it really on the market. But indeed, you made the point. It's really a competing technology, has some advantages. If you look at the PEM fuel cell, we have the potential of really mass produce everything like in wall-to-wall processes where you really can get very, very inexpensive. If you look at the raw materials we are using, and if you look at the scalability, there are a lot of advantages, but we cannot really play out those advantages at this point of time when we are talking about 10, 100 or maybe 1,000 systems. We really need to talk about big numbers, and then the situation might change again.
And for these big numbers, you can provide the manufacturers with MEAs. How are they built up nowadays, the MEAs you offer to your customers?
Well, it's a 5-layer MEA, so obviously we have the membrane, the core or heart of our MEA based on PBI, and heat-resistant polymer and phosphoric acid. Then we have our catalyst layer and the gas diffusion medium, and also a sub-gasket to provide long-term stability and also better way to handle them. So that's not really unusual. You find other MEA designs that are quite similar.
So, but this all consists on a woven construction, on a woven electrode, doesn't it?
Oh, this is indeed true. Yeah, currently we are using a woven gas diffusion material that we coat with carbon material, with a paste, MPL, and then with a catalyst. And if you look at our products right now, the P1000 and also now the P1100, that's based on the material. We have a lot of experience with it, more than 10 years. But subsequently, or if you look into the next years, we understand that we really have to change to other material, low-cost material, paper-based gas diffusion electrodes. That's the way to go when we really want to produce not only a few thousand square meters of this material, but 10,000 or maybe also 100,000 square meters.
So what you brought to this fair is your P1100 MEA, which are still on a woven material and even made better and increased in power density maybe. But in the future you will have completely different MEAs.
Yeah, it's really a big challenge, and we are working on it already now for 1.5 years to develop this new MEA generation. And we hope to be here maybe next year with like the first MEAs that we can give to our customers. But currently we are really glad to introduce the P1100, which when we developed this product or this improvement, our intent was to improve the uniformity of the GDE and also the producibility. So we wanted to debottleneck our coating capacities. That was our intent, and it really turned out in the hands of our customers that those MEAs also have a rather large performance improvement as well, which is perfect for our customers, certainly.
I can imagine that. If I imagine a MEA, it has to be very thin, and the electrodes have to be easily switched through it. And if it's the thinner, the better. So paper can be much thinner than a woven material.
Yeah, it's rather what we are looking in is the uniformity of the material. You mentioned the thickness, that's one of the parameters, but the whole structure, the morphology of the material makes it easier to have always the same, and that's what we are looking at. I mean, we don't need necessarily another millivolt or more performance. We rather want to have always the same product, and paper material helps a lot to get this way.
But is it as robust as a woven material, or is it easy? You know, could be easier, like torn away or something like that. Yeah?
Well, that's actually a good point. We have to readjust and to change our processes and our customers as well. Handling will be different. That's certainly true. But it's a material that, I mean, in many sectors in the automotive industry, that's a typical material. So it can be used and it can be managed. And we have made a lot of good experience so far. So we will have to adapt, but it can be done.
I think it's an interesting process because you have a product, you have a lot of customers, they're already waiting for more products, you can't produce as much as you could sell, and then you tell your customers, okay, we finish this product, we give you another one, and say it's better, and they believe it.
It is difficult. It's an industrial or a business and industrial decision. We believe that with the sort of current technology, we will end up in a dead end. So we can produce, we can improve, but at a certain point we will not be able to either provide the quantities that are needed in a few years, nor achieve the cost targets that we have set ourselves. So we have to go now one step back to sort of reinvent our technology, really start sort of really a next generation, not just some incremental improvement, but really does another step. The same holds true actually also for the MEA production technology. We also have to go one step back and think about how to really make it more cost efficient.
And it's a completely new technology if you use paper now. So do you have the expertise in gas diffusion layers in this consistence, or do you seek for new alliances?
That's an excellent point. Yeah, I mean, if you think of BASF, yeah, certainly this company has a lot of money and a lot of resources and could do it, but it wouldn't be wise. It's much more efficient and smart to look for a wide industrial partner, a company that has the expertise and that has also the industrial capacities to produce in vast quantities, and that's what we have done, and so our development is with such industrial partners.
It is for me very interesting to see an industry like yours growing, and also the things that have to be changed to make to find the cost targets and how to take the customer with you. I hope you're very successful with that. If you have any questions, just feel free to raise your hand. I will come with the microphone right to you. Otherwise, I would like to advise you to visit Dr. Henschel at his booth, which is number D66, just over there, and visit him and discuss the next generation of MEAs with him and the advantages that are given with it. I would like to thank you very much, Dr. Henschel, for this interesting talk, and I would like to thank you for your attention.
Thank you.
Pleasure.
Ja, machen wir es mal so, dann übergebe ich Ihnen das.
Okay. And there's the next interview on stage here in a few minutes, which will be with UTC Power from the United States about stationary fuel cells for combined heat and power production. Katrina Fritz Intwala will talk about it in a few minutes here on stage. I'm looking forward to that.